Hello and thank you for having me here. My name is Camilla Vael, as I was kindly introduced by Balthasar before, and I'm talking today about temperature-dependent dynamics of reversible electron traps in especially super yellow. Now, this is another topic than we were before, so no TADF or something like that. So we are focusing here now on trap states. Trap states are widely looked into because they usually have a very detrimental effect on our full devices, and especially electron traps seem to have a really major effect on the electron mobility in most of the semiconducting polymers, and this is attributed to several kinds of electron traps, and one of those, which is quite notorious, is the, where is the laser, by the way? Ah, yeah, okay. One of these trap states is the water and oxygen-based trap state at around 3.6 electron volts below the vacuum level. And most of the polymer usually have a LUMO which is above this level. So this is in fact a trap state which lies in the gap between LUMO and HOMO and contributes to the slowing down of electrons inside those kinds of polymers. Also in the polymer I used, that is super yellow, we expect this kind of traps because we have a LUMO that is higher, and we have a difference between those kind of trap states and the LUMO of about 0.65 electron volts. Now, the reason why this is important is because during our studies, we noted that when we apply a constant current of about 10 milliamps per centimeter square in our case, we not only can observe the increase of device voltage due to hole traps, but also due to a kind of electron traps with a trap depth of about 0.65 electron volts, which suspiciously sound close to the electron trap which usually is present in most of the polymers. And so how can we distinguish between the hole and the electron trap? Well, what we can see is that the hole trap development takes place in a very long time frame. So if we reduce the time frame to only a few minutes and we use a rest time in between, what we can see is the development of electron traps and also the decay of electron traps. This is something curious because usually when you have degradation due to formation of traps, you don't expect to have a decay of trap states. And just to see that we don't have a substantial amount of hole traps forming, this experiment took place in about the same time frame as this experiment, and we have a lower increase in device voltage. And also what we can see is a significant recovery when we rest the device and do not apply any constant current. Now the question is, okay, we know the energy of these trap states, but how many of those trap states are developing during this experiment? And it's not so easy to get from this measurement to our trap state density because it's not directly extractable. So what we have to do is we have to apply some kind of model, and we decided to take our stack and make a very simple electric stack consisting of just the p-dot layer, the super yellow layer, and the calcium layer, and do drift diffusion simulation to get to the number we want to extract. But the thing with drift diffusion is it's usually based on constant voltage experiments or simulations and not on constant current. So in order to simulate this trap site density, we have to include an extra step, and this extra step consists of just trying to optimize the simulation to get a specific constant current, in our case this 10 milliampere per centimeter square, and this has to be done by optimizing or manually just shifting different parameters. And one thing here in particular is if you want to do this, you have to change at least 2 parameters at the same time, because if you change one parameter, which has influence on the current will either increase or decrease, so you have to take another parameter to compensate for this change in the current. And the pairs we used for these simulations is the electron and the hole mobility, or the barrier and one of the mobilities. And when we do that, we can get to our basic baseline of 10 milliampere per centimeter square. And when we reach that, we can now simultaneously increase the voltage and the amount of trap states, just to see how many trap states we need to reach a certain voltage. When we do that, we get this kind of graph, and we can get the number we are looking for, the trap site density at each voltage. Okay, so we did this kind of simulation now for all kinds of temperatures that were available for us experimentally. And here on the left-hand side, I show you an experiment where we just stress the device for 5 minutes at 10 milliampere per centimeter square at 230 Kelvin, 270, 300, and 330. And one thing that is notable is up to the temperature of 300 Kelvin, we have an increase in voltage. So the higher the temperature is, the higher the voltage increases. This is only true up to 300 Kelvin. So if we go above this, what we have is a slower increase in voltage. This is something for later. Now we can actually simulate these results, and we get the graph here in the middle, so it's quite close to what we measured. But when we take a look at the trap sites that are developing, we can see that we have a monotonously increasing number of trap sites. So the highest density of trap sites evolve at 330 Kelvin. Now, why is there the difference between 330 Kelvin being not the highest, but having the highest trap site density? Well, one of the reasons is that we can get quite close to the glass transition temperature at 330 Kelvin, and it is possible that we start to have significant changes inside the device as well. So we don't need to increase the voltage as high to have an effect from the trap site. Now, one thing that we also noted while doing the simulation is that we have quite a high dependency on the parameters we choose. So here just show you 2 parameter variations we've done. So on the left-hand side is the same graph I showed you before. We have here a fixed mobility ratio between electron mobility and hole mobility of 1 to 10. And we also fix the capture rate to this number to 5 times 10 to the power of minus 13 centimeter cube per second. And in another simulation, what we do is we take the same mobility, but we calculate for each of the mobilities the associated capture rate. Now, when we do that, what we can see is that we have an increase in trap site. We have to add in our simulation. That is up to a factor 5 higher than in the case where we have a constant capture rate. And this is quite a significant difference, and this already shows that we cannot pinpoint the number of our trap states directly. So just to show you the difference between those 2 simulations in numbers. So what we used here is the mobility for holes, which is 10 times higher than the electron mobility. And this mobility was derived by just fitting the mobility to the experimental voltages we measured in our experiment. And what we can see is that we actually have an increase of the mobility, which corresponds to an activation energy, which is exponential. So this is exactly what we expect for our device. Now, this capture rate, of course, is only for the second simulation I showed you, because in the other one it was constant. But what is important to note here is that the capture rate for holes of the electron trap is 10 times higher than the capture rate of the electron trap for electrons. This means that we have a quite efficient Schocker-Reed-Hall recombination, and this means we have very little field trap. This in effect means that the number of trap sites we have to add in our simulation to see an influence on our current is significantly higher, and this explains the difference we can see between those two simulations. Now, another question that is important is to see we have electron traps which develop slowly over time. And it takes longer than we usually would expect for electron traps to be filled. And the question is, why is it that much longer? So we are talking about a difference between 200 microseconds to about 1 second to 15 minutes. One of the theories we have is concerning this complex here. So it is consisting of 2 water molecules and oxygen molecule. And when it has electron captured, it is quite stable. These are the 3.6 electron volts we usually find. But when we remove this electron, what happens is we have a very, very unstable complex which has an energy of about 0.016 electron volt. And just as a reminder, at 300 Kelvin, we have an energy of 0.026, basically, meaning that this complex will dissociate quite fast. So in order to actually get a trap, we need to start from the components, basically meaning that we have a 4-body reaction to form a trap. And the chances of that happening at the same time is not very high, which increase the time of trap formation. This theory has to be tested thoroughly, and we started with kinetic Monte Carlo, but we haven't yet conclusive results, so and I'm running out of time, so I have to come to the conclusion. We modeled the voltage increase in our drift diffusion simulation with an increase in the number of trap density, and the density we got from the simulations corresponds to the density of trap states we would expect for this kind of trap state at 3.6 electron volt. And what we also could see is that the trap formation rate increased with increasing temperature, meaning that actually a diffusion process might be viable. And also we saw that the number of extracted traps is very dependent on the input parameters. So what we can say is maybe we have this diffusion of oxygen and water molecules as a process for the trap formation, and we need to investigate this further. And at this point, I want to thank my colleagues at Fluxim and Vael for preparing the devices, and Roland Hani and Frank Nürsch for their support. Thank you.
Thank you, Camilla, for your presentation.